it's time to tear down this projector. Just in case you missed my previous videos, I'll just go over a quick overview of the projector. This projector mounts to that lamp house, which contains this 5 kilowatt xenon short arc lamp and an elliptical reflector. The light from the reflector comes in through this hole, through the shutter, through a dowser to cut off the light before the start of the show, through the film inside here, through the lens and onto the screen. There are two lenses, one that projects the image normally, and one that compresses it vertically for wide anamorphic images. The film comes in the top, through the film gate where it's projected. It's pulled intermittently through by this intermittent sprocket, stopping once per frame to be projected. It comes down through another roller, then through the audio reader, which reads the audio out a set distance after it's projected, and then the film goes out and onto the platter for take-up. The shutter rotates once per frame, cutting off the light twice per frame to produce a 48 Hz flicker, which is less objectionable. The whole projector is driven by a 1800 RPM half horsepower synchronous motor. I would have thought they would have used a closed-loop speed regulation system with a DC motor, but I guess the basing it off the line frequency is okay in this case. I'll just give this a quick run here. There's the intermittent sprocket, which is sort of stationary, and there's one more rotating sprocket down here, and there's the shutter. And here it is from the gearbox side. See the oil spraying down up there from the oil pump. The build quality on these units is incredible. You just look at the thickness of this casting in most areas, and this spacer block here is solid aluminum, so they obviously weren't too concerned about costs. Before we get started, let's just drain the oil. Now, which way does this turn? There we go. Okay, let's see how easily this is going to come off. I wonder if they've put any, so they may have put silicone on this to stop oil leaks. Oh, no, not going to be too hard. There we go. Let's just stop any drips. Starting from the motor here, there's one belt that goes back and drives this shaft here. This one actually directly drives the sprocket that is in the audio reader. And from that shaft, another belt goes up and drives this input shaft. That's coupled through gear down in there to this main vertical shaft, which pretty much drives everything. It also couples to this oil pump down here. Starting at the bottom, this drives the lower film roller that pulls film out after going through the intermittent sprocket. This thing with the flywheel attached to it is the actual mechanism that generates the intermittent motion from the for the intermittent sprocket. That I'm very interested to see exactly how that mechanism works. Next is the shutter. You can see the shutter disc with a cooling fan in there spinning, and that's the top input sprocket. And this little vein on the top that flings oil around coming from that tube and it goes down to the oil pump. And it looks like there's a little catch thing to catch the oil, some of it, and it drips it into a set of gears in here for the intermittent sprocket. I don't know if you can see that in there. The framing control adjusts the phase of the intermittent sprocket. That basically just turns the entire mechanism there. And it also actually adjusts the phase of the shutter. When as this turns, you can see there's a right near the center, there's a cam that's being pushed up and down. That moves a little piece up here that pulls this piece back and forth. And if you look right in that spring, there's a sort of a helical gear. So as this gear here is pushed in and out of that helix, it changes the rotational phase. You can see the shutter moving as we move the frame control. I think that's needed because this, as you rotate this whole thing, it throws the phase off, so it has to be corrected here. It's actually quite ingenious. And there's another little control up here. Just spins this gear, which is adjusts the phase again. I guess that's to trim the exact phase right so the film isn't moving while the shutter is open. This large flywheel here is actually not connected directly to any of the drive system. This goes to the roller that stabilizes the film as it goes through the audio reader. Because if the film changes speed at all while the audio is being read, it would change the pitch and cause distortion. It looks like this central assembly containing the vertical shaft will be relatively easy to remove, so I'm going to give that a try. Hopefully the whole thing will just unbolt and come out. Let's see what's inside this oil pump. Oh, it's a little rotary pump, sort of like a refrigeration compressor. Nice. There's the copper gasket. And it's very simple. I like this design. If you look really closely in there, the vanes are pushed apart by a little tiny spring. They're not just held up by centripetal force. This probably doesn't spin fast enough for that to work. And on this side we've just got a little strainer. Doesn't seem to be much on that. If we can focus. Yeah, that's pretty clean. Kind of an elaborate oil distribution thing. This is actually on the suction through this little block and then into the pump. I think there's a little hole right here. There's a little hole where oil, I guess excess oil comes out. I guess they didn't need the full output of this pump. Okay, now we're starting to see some clever stuff on this intermittent drive. The main shaft drives this shaft here, and the gear drives this gear on the flywheel. The flywheel drives this shaft, which actually drives the intermittent mechanism. And you can see there's a little cut on the shaft there, and that takes oil in. The oil drips down from this onto the gear, is pulled around. It's probably forced into the center where it gets pulled in by that groove and pulled into the mechanism to keep the mechanism lubricated well. It's quite a good design. Looks like to get this out we just need to get that plate off, and there's another one on the other side under this gear, so I just need to loosen these screws, take the gear off, and the whole mechanism should slide out so we can disassemble it. Okay, here it comes. Oh nice, the whole assembly slides out nicely. Now we can, yeah, if we turn this, that's working. There we go. So that's how it works. Yeah, this thing spins and it grabs this the pin, grabs these little into these grooves and drags it along a quarter turn each time. Nice. Too bad we can't see this working while it's open. That would be quite cool to see. If you actually think about it, the amount of stress this thing is under is quite incredible. The intermittent sprocket accelerates from 0 to about 3000 RPM in 5 milliseconds, and then goes from 3000 RPM to a stop in another 5 milliseconds. And it does this 100,000 or 200,000 times every movie. It's amazing these things last as long as they do. Here's the main electrical junction box. Bottom just has a bunch of wires for connecting to the motor and other 120 volt things. There's a transformer and a board with a bunch of relays that must control all the motors that drive the automatic lens changeover. And this bunch has a couple of switches and a board that looks like it has a programmable device, which I find a little bit surprising. Pull off this sticker, see what this is. Motorola MC6 something. Peel it slowly so it doesn't rip. It's still. '68HC 705. Looks like it's running at 2 megahertz. Okay, power is connected up. Let's see if this thing actually works. Oh, it's doing something. Nope, that's not right. Something must be wrong with one of the sensors. Yeah, something's definitely not working right with this. Let's see if we can fix it. Looks like they're using Hall sensors to determine the position. There's 2 magnets here. If anything, this is probably what's stopping it from working. I'm not sure what I did there. All I did was remove this PCB and put it back in, but it now works. If I push the button, oh, it's already on that. If we go the other way, I think that back and forth at the end is just to make sure this latch part is solidly down and the lens is in the exact right position. The one thing that is not working is this this motor that drives this plate back and forth. Wonder if it's just not getting a connection or something. Looks like the problem with this motor here is just that the wire had fallen out, the black wire had fallen out of the IDC contact. So now it should work. Yep. And here's the automatic dowser. Nothing too special in this box, just a couple of intermittent duty rated solenoids. Well, that was surprisingly easy to get out, just one screw. Here's where the actual image is projected from. These little bands keep the film pressed nicely against the sliding film gate here. Little rollers to keep the alignment just right. Little LED light in there that allows you to set up the framing. This is a multiple number of frames offset from this, so you can frame it up here easily. Little DC gear motor in there to drive the plate back and forth. And on this side, the only thing we really have is this water cooling block to remove all the heat from the stray light hitting everything. The shutter here looks like it's made of cast aluminum, and there's a little fan on the back to help dissipate heat. The shutter dissipates something on the order of a few hundred watts, so it gets quite hot. These higher power projectors with the 5 kilowatt lamp also have this auxiliary fan that blows air in this hole down here. Apparently the ones with 3 kilowatt lamps don't have that. Just to get some idea of how much light is hitting this, you can see this dowser plate is almost melted from the heat, certainly discolored. And here's another view of how the shutter phase is adjusted automatically as you adjust the frame control. Got a lot of engineering went into this thing. This little plate the film runs on is also very easy to take out, just one set screw and it pops right out. Here is the audio reader. The film comes down after being projected, goes around this roller here. This is a big weight attached to it. If we go around the back, we should be able to see this spinning. Yeah, there's that wheel spinning. And that's there to keep the film speed very steady as it goes over the analog audio reader. If the film changed speed, the pitch would change. There's also a tensioner on a little damper thing. And then the film goes over a final roller and out. The audio is stored on the film as 2 tracks, an analog track on the right, which is, you can see like a waveform like on an oscilloscope, and on the left side between the sprocket holes there's digital code, sort of like a QR code. Those are read by a line scan camera. Okay, this lighting head just has 2 really small linear array LEDs on it. I wonder if those are separate dies or if they're just one big die. They have little flat cables, flat PCBs going off to connectors. And it looks like the angle of either of the LEDs is individually adjustable by loosening these screws and twisting these little bits. Okay, so you can focus, get them aligned with each camera. On closer inspection, these LEDs are definitely a whole bunch of individual die. And it looks like they may have a whole bunch of groups of 2 wired in series. Here are the 2 audio reader cameras. This one's probably just going to be 2 photodiodes to read the 2 analog channels. And this one's going to be some sort of an line scan camera. If you look in there, you can see a ceramic dip with some material to block light from getting in. And judging by the lack of stuff on this, all the driver electronics are probably on the remote system, the remote Dolby decoder. So it might be difficult to get this working, although I'll take a look. If there's enough, perhaps there's enough readout stuff integrated onto the line scan chip that we could at least get some sort of a signal out of it. Okay, there's another board in there. That must have the actual sensors on it, so we're going to have to get that out of there using hex drive and Allen wrenches on this one. The screws they're using have little spring washers on them so they, that you don't put too much force on the board. And we should be able to pull this out now. Come on. Am I missing? Oh yes, I am missing something. There's little set screws here that have to come out. There we go. Oh, look at this. It's a nice sensor. Some sort of a large single die in there. Some sort of a linear photodiode. What do we have? Just 3 pins. Yep, just ground and 2 signals there. And TL072 op amp. What does this say here? Model OSPA2 by Component Engineering. I just noticed that there is no cover glass on this. This die is directly exposed. I know they have glued over the wire bond, so it's not too sensitive, but still I would have thought they would have put glass on this. And this sensor is part number 270010029806. I think I see what they're doing with these little screws with springs on them. These never fully clamp the PCB down. It's left sort of able to move around left and right a bit in those slotted holes. And then you trim it left and right using these set screws on the side. It's actually quite a nice way of doing it. And this board just has another op amp on it, probably just amplifying the signal more before sending it out to the whatever is next in the audio chain. That tape seems to be breaking loose. Oh, and the jumper fell off. There we go. There's the linear sensor made by Dulsa. I've heard of them before. Model IL-C3-0512B. You have to look up the datasheet on that and see if we can drive it. What else have we got on here? What is that? EL7212. Haven't heard of that before. Some other, what else? DS26C32 and an LM618. Okay, I found the datasheet for this image sensor. This is a Dulsa IL-C3 series linear CCD. This one, the 0512 means it's 512 pixels wide, 1 pixel high. These are read out with 2 parallel analog outputs at 30 megahertz, so that's 60 megapixels per second, which gives about 100,000 lines per second on this particular sensor. And the reason the package is seemingly unnecessarily wide is because they make other versions up to 2048 pixels wide that look sort of like that. And these two parts are 2 amp dual power MOSFET drivers. Those are used to drive the clocks for the sensor to clock data out of the CCD. This is a quad differential line receiver. These two parts are 100 megahertz, 100 milliamp output op amps. Those probably buffer the output from the CCD as it's being driven onto the cables. So there's a long run to the video processor. And this is just some 74 series logic. The other side, just a bunch of passives, various filter caps and coupling caps and resistors and things. Also got a bunch of resistors here on the input. Maybe they're termination resistors for the cables, although that's possible. We also got some diodes filtering them as well, clamping them, I'm assuming. Unfortunately, it doesn't seem like it'll be practical to run this. There's too much of the control electronics is off in the in the audio processor itself. It would be a lot of effort to set up something to actually run this. I'm wondering if these sensors were used for, or even originally designed for, reading the analog audio tracks, because the first thing that came up when I searched for this online was this Dolby patent from 1991 that describes a method of using the output of this these sensors to read the analog audio tracks in a low noise manner, and it actually specifies in the patent this particular part number. On the bottom of the sound reader there was also this unit mounted, which seems to detect the presence and motion of the film. Let's see how this thing works. Looks like the presence is just detected by a couple of little optical sensors here. That's easy enough. But there's this potted assembly that I'm curious about. It's right next to this roller. There doesn't seem to be any magnets or anything in this roller, so I'm interested in what this thing does. Okay, this potted module is out, and there's actually quite a bit of stuff in here. A whole bunch of chips that I don't recognize the part numbers, except maybe that C series there. A whole bunch of relays on the output. Yeah, just connection up to the optical sensor board. Let's see what some of these chips do. Okay, this ULN 2001 is just 8 FETs and freewheeling diodes. Those are obviously relay drivers. These two are 4000 series logic, and I should have recognized the 339. These are just quad comparators. Okay, so okay, there we go. Looks like it has some coils in it. Yeah, little coils in ferrite connecting down to something, some electronics in there. Some sort of magnetic based sensor, it looks like. Let's see if we can get down further and see what electronics are on this side. Doesn't look to be too much in this, just some passive stuff. We can't really see in there too well. But yeah, it doesn't look really, there's nothing really that special or interesting in this. I'm a little bit puzzled as to what this thing is actually trying to detect, because this roller is non-conductive and non-metallic. There's no magnets in it. The film is non-conductive and non-metallic. My best guess is this is to detect some sort of piece of metal tape you would put on the film, perhaps used to turn the projector on or off, because it would the metal going near it would affect the Q of these coils. If anyone knows what this is actually designed to detect, please let me know. It looks like my guess was actually right. This found the datasheet for this. I probably should have looked up the datasheet first. But this is a Q detector for the automation system, and it detects little, exactly as I thought, it detects little bits of foil tape placed on the film. There's 3 separate ones for 3 different cues. And I think that concludes the teardown of this projector. I'll just finish putting it back together again and mount it on a stand for display. And stay tuned for the next video where we'll tear down this 7 kilowatt xenon short arc lamp power supply. Anyway, I hope you liked this video. Thanks for watching.